and I'd like to introduce Professor Stephen Sillett. He's a professor at Humboldt State University, and he has the Kenneth L. Fisher Chair there. Now, Steve is someone who is, I consider, fearless. He's willing to do things up above the trees, many hundreds of feet above the ground, that most of us, we'd probably have a heart attack if we had attempted it. So, Steve?
I heard that. Could we get these lights a little dimmer, if possible? So, if you're like me when you walk up to a big tree in the forest, you have a lot of questions. You look at it and you go, how big are you? How old are you? Or maybe you'll be a little bit more sophisticated and say, how's it going? What have you been up to lately? And the thing is, from the ground, it's really difficult to get answers to these things. And so we've had to climb them. And I just want to start out by saying what an extreme privilege it has been to work on this project. We have got, this was a photo taken when we first started it in 2009. And our very first tree was that one on the right. And what a journey it's been. And I just want to tell you what we've learned about these trees, because we've been asking questions, a lot of real basic questions about these trees. So as a synopsis of our study areas, you've seen the map. I've rotated it slightly. But I wanted to point out the gradients across which these plots are located. There's a pretty strong precipitation gradient from north to south in the Redwoods. Places in Del Norte County that get over 2 meters of rain annually on average, to places down in Big Sur that get less than 1 meter of rain. And then, of course, the giant sequoias aren't nearly as wet. There's also an elevational gradient. Of course, the coast redwoods are lower, the giant sequoias are higher. And that's going to have a lot of implications for their performance. So let's start with giant sequoia. And I thought the best way to start out would be just by taking you through the rogues gallery of these characters that we've gotten to know over the last 4 years. So I'm going to show you a series of diagrams of these trees based on our direct measurements from climbing the trees, measuring their trunks at all heights, measuring each branch, basal diameter, height, angle, slope, distance. And I'm not going to reveal the ages of these trees yet. We have estimates of their ages, but I want to save that because I think it's important for me to explain exactly how we determined how old they are, or at least how old their minimum age must be. So starting out from youngest to oldest, giant sequoia, there's 3 slides showing them. So these are the relatively young ones. You'll see that they start out, they're mostly crowns full of branches, which are shown here in green. And these are the foliage-bearing portions of the tree. In addition to measuring their crown, the main trunk, and their branches, we also do a detailed analysis of their basal footprint. And Allison mentioned that it's irregular near the ground, and this becomes more and more the case as trees get bigger. I want to point out here's a tree who's snapped off, and this red is a reiterated trunk. So in these diagrams, the red are what we call segments, and they're basically pieces of wood whose base and top we've measured. And from those come branches. Getting a little bit older in giant sequoia, you see they get more interesting. You also see they get quite tall. Here is the tallest known. A tree that miraculously seems never to have been struck by lightning. You can see that giant sequoia has big reiterated trunks, big limbs. These 2 trees are old, but not very big. Moving on to the next group, the true monsters. And you can see a lot of variation. And the thing that you notice as you move through this rogues gallery is how individualized they become and they get old. We'll be talking a bit more about that tree on the right in a moment. It's this one. So let's shift to the coast redwoods. So same sort of thing. Go through we had 32 giant sequoias that we crown mapped every branch, 55 coast redwoods. So from youngest to oldest here again, you see that like the giant sequoias, when the coast redwoods are young, the crowns are pretty basic. A lot of branches, pointy tops, not a whole lot going on. But you will also notice some trees in here that are remarkably small and kind of oddball. These are suppressed trees, overtopped by taller neighbors that are kind of languishing there in the understory. And moving on to some of the more interesting trees, a couple of these things I just have to comment on. This tree here, tallest tree in Marin County, what a nightmare. Forked top, every branch downsloping. I just had such a heck of a time dealing with that tree. This tree, insane. There's 1.2 kilometers of trunk length in this tree, not counting the main trunk. It took us 260 hours to map the crown of it. Here's a tree I actually almost lost my mind in. It's actually a double tree. There was a crisis, a psychic crisis, when I thought we'd gotten off on our notes, and it was like a 10-hour day, the fourth in a row, and I was like, we have to start over. But it was fine. And then getting to the oldest and tallest trees, there is, in fact, the champion, which is interesting. It has the deepest crown of any tree on Earth. Live crown over 300 feet deep. And again, you can really see the individuality of these trunks in their footprints. And it was important to do these footprints because there's a lot of wood down there. And if you just stretch your tape around a tree like this, you're going to have gross overestimation of how much bark and wood there is. Okay, so that's the rogues gallery. Now, we mapped all these branches in the trees, not just to generate a three-dimensional model, but we wanted to know how many leaves the tree had. What was its photosynthetic capacity? How much bark? How much cambium? How much sapwood? So all of these branches were mapped. Each one visited and measured. Here's Giacomo Renzullo doing some measurements in the tree in Redwood National Park. And he's actually measuring a segment, piece of wood, where we're basically modeling as a frustum. We get the top and the base, and then the branches come off of it. So of the coast redwoods in the study, we had about 12,600 branches mapped. You'll see a hard cutoff here. This is just simply a size class, 4-centimeter diameter. Below that size, we typically just counted them in multiples for 0 to 2 and 2 to 4 centimeters. There was about 25,000 of those that we counted. Occasionally, unfortunately, we would knock them off, so we would collect those. And these are the ones that we actually dissected, removed from the tree, and processed, which I'll explain shortly. And you'll see that we spread our destructive sample out across the full spectrum of height and diameter that these branches exhibit. And the goal here, again, is to develop comprehensive equations to predict all of the quantities above ground in the tree that are measurable and interesting. So that's coast redwood. You'll see our biggest branches, these again would be the green things in those diagrams, were less than 40 centimeters in diameter. That's a pretty good-sized branch. Giant sequoia, even bigger. So here's Cameron Williams and Russell Kramer out mapping a big limb system. You can see a reiterated trunk with many branches of its own, this giant series of segments, and this is a dead piece, mapping them. And so here's this 8,000 giant sequoia branches that we mapped. Again, you see the hard cutoff from the size classes. We get into some of these little trees, and if we had a 4-centimeter diameter cutoff, we wouldn't have mapped anything. It would have been great, easy, but we wanted to get higher resolution on those. And then here's our set of branches we removed. And you'll notice that we stopped at about the same size that we got in the coast redwood. And the reason is because these branches here, very few out of 8,000, there's very few legitimate branches. And that's basically, it's something that hasn't broken and forked at some point in its life. There's very few of them. But when we started looking at these things, it's like, you know what? I don't think we're going to deal with this. And the other thing was they're over 1,000 years old, too. So we didn't. So instead, what we did was we broke them down into segments. And so there's very few things that are really big in these trees that we didn't do a very fine-scale analysis into smaller parts that then we could develop equations to predict. So this is a summary of the size class distribution of appendages. Now, by appendage, all I mean is things coming off the main trunk of the tree. And so I've just done a frequency histogram of each species by appendage diameter. So the number of appendages in each size class is displayed across the top of each. So you'll see that among branches, there's very few branches in Coast Redwood over 30 centimeters. Beyond that, things were broken up into segments. They were called a branch segment if it was just a forking complex of branches. They were called limbs if it was a branch-like segment that gave rise to trunks. Very few really huge appendages in Coast Redwood. But look at giant sequoia. You see some major differences. So there's these few that are bigger than the 40. The rest of these branch segments we were able to, or branch systems, we were able to break down into smaller pieces. But you'll notice that there's a lot more reiterated trunks in yellow in Coast Redwood and a lot more segments of limbs in giant sequoia. And I think you'll see that when I go back to the rogues gallery in a minute. So then we had to do the dirty work of selecting these branches, 257 in total among the 25,000 that we mapped. Remove them with a handsaw, and we did good arborist cuts. So this wasn't sloppy work, but we didn't want to lose anything, not even a cone, if possible. And then these were taken to the ground and painstakingly cut into pieces and sorted by diameter class, and all the leaves plucked away. And subsamples of the leaves put in plastic bags, put in the refrigerator, taken to the lab for scanning, further dissection, and counting. So there's a whole team at work at Freeman Creek, the Sequoia National Monument. And then lugging the subsamples back to the lab, where they took a lot of time to dry. You'd be surprised how long it takes a piece of wood like this to dry to a stable mass in an oven. We're talking months. So we got them all dried down so that we could basically put everything back to dry mass, and then from there extrapolate to the total. So we developed equations to predict the dimensions of the branches of these trees based on the complete inventory of branches that we made while we were mapping the trees. So here is the final equation for Coast Redwood branch dry mass. I'm just going to show you a few examples of these equations. But this equation wasn't bad. The predictors are the diameter and the path length of the branch. Path length is the length along the woody piece of the branch. So we're predicting all but about 4% of the variation in total mass with just these measures. Then these equations can be applied to all the branches that we didn't cut from the trees, which is 99-point-something% of them. Equation for giant sequoia. It works pretty good. 98% of the variation. Our predictors were path length and diameter again, but also the number of foliar units. And what was cool about giant sequoia, well, there's lots of things cool about giant sequoia. The foliage is produced in these very discrete, countable things. It's about as big as a beanbag chair. You remember those? So we were able to count them. And that was a really good predictor for things like total mass, leaf area, and a bunch of other variables. So we had equations like this that were developed from our destructive sample to predict almost every quantity that you might want, including number of leaves, surface area of bark, volume of bark, surface area of cambium, volume of sapwood, volume of heartwood, deadwood, heartwood, everything. All right, then we can sum them up. Now here on the x-axis, I have the main trunk Btb. I'm going to be using this term a lot. This is diameter at the top of the buttress. DBH should be thrown out the window when it comes to big trees. It's just no good because it's so irregular, as you can see from those footprint diagrams. So we found that the single best measure of a tree size was its diameter above all that, to where the trunk becomes more or less columnar. Now, on a little tree, DTB is actually below breast height. But on a big tree, it could be 8-9 meters off the ground. So you might need a ladder to measure. So what I have here is trees. This is trees separated by trunk size. So here you have 5 coast redwoods greater than 350 centimeters diameter at the top of the buttress. And what I'm showing is the proportion of the masses of appendages in various categories. So when the trees are small, vast majority of their appendage mass, and again, appendage is everything but the main trunk. The vast majority of their appendage mass is in branches. As they get bigger, a greater and greater proportion of their appendage mass goes into segments. And that makes sense as the trees become larger and more complex. And you can see also this group here of small redwoods that are actually, they have something going on. These are those little trees in that rogues gallery I showed you that had been suppressed. And they're actually quite old for their size, that had a lot going on. Again, you can see a difference in the two species in terms of the relative balance between trunks and limbs. Okay, here's the Btb summary that Bob prepared. So basically, yeah, this is the standard measure, but it's, you know, and this becomes especially problematic in trees that have fire-scarred bases, which we found a lot of. Btb is right above that flared base. And again, the height of the top of the buttress varies, but it can be precisely determined. So you'll see me using DTB and DBH a lot. Turns out that after we got all of these numbers assembled for these trees, and we could then add up all of the predicted values for the trees based on those equations, we could then come up with whole tree numbers. And these predictors from the ground or near ground would be very useful. But because we weren't felling these trees, there's a lot of parts of the tree, particularly those segments and reiterated trunks in the main trunk, for which we don't have good data unless we do some destructive sampling. So initially, the coring that we did was designed to get at some of these things like the thickness of the bark, the thickness of the sapwood, so that we could distinguish between bark, sapwood, and heartwood in our model. And you can also take these cores and figure out the wood density and even the bark density from other samples so that you can transfer volumes to masses. So this is how we approached the larger elements of the tree so that we could get whole tree numbers. So this is the equation for coast redwood that should stand for quite a while as the best prediction of its total above ground dry mass as a function of variables that you can measure from the ground or with a ladder. You see that the two strongest predictors are diameter at the top of the buttress and the functional diameter. Now you know these footprints that I showed you in the rogues gallery. Functional diameter is converting that cross-sectional area to a diameter of the circle with the same area. So that's why I put that little F in front. So just using DTB and DBH for coast redwood, of any coast redwood in an old-growth forest, you can predict 98% of the variation in above-ground dry mass. Now, if you need some applications, this is not good enough. You need more precision, more accuracy. How about this one? Now, that's not bad. So if you were, instead of just measuring DTB and DBH, if you actually mapped the whole main trunk by taking diameters all the way up, added up the total volume, measured all the reiterated trunks, found out how much heartwood volume there was in the tree from the increment coring, and quantified the crown size, you can predict a lot of the variation. Now, if you need more precision than this, you have to map every branch, which I don't recommend. Now here's the giant Sequoia equation, a little bit different. It still has DTB. Again, this is really a great predictor. It also has crown volume. Crown volume can be measured from the ground as crown radion, total height of the tree, height to crown base, and you have to pick a shape, either a conic, a paraboloid, or a perlate spheroid, depending on the shape. But from the ground, you can measure these two variables and predict all of about 1% of the variation in total above ground dry mass. But if you need more precision than this, you can measure not only the crown volume, but the main trunk's total volume and the surface area of the heartwood deposition zone. Tom Warner was here. I saw Tom. You remember that tree we climbed in 2007 for you? That's this one. And the reason it's below the line, it has less. Its actual measured mass is less than predicted because the upper crown was in serious decline, which is why Tom wanted us to climb it because it was a hazard. But otherwise, it's a pretty good relationship. So, to answer this question, the simple question, how big are they? Well, for coast redwood, turns out that the two biggest ones, this is the giant Sequoia and that's the coast redwood, they're actually about number 2 of each, but they're darn close to being the biggest. These are their masses in metric tons. That's megagrams. Metric tons about 2,200 pounds dry weight, over 1,000 cubic meters of volume, half a hectare of cambium surface area, nearly a hectare of leaf area in this tree over here that you can't see, and over 1 billion leaves. Of course, the giant sequoia leaves are smaller. Coast Redwood's got more leaves. Now, a lot of people, when we talk about size of the tree, is big or is it tall? Well, they're not the same. And neither of these two champions are the tallest tree. The tallest ones are actually quite a bit smaller in terms of their total volume and mass. But there they are. It's pretty tall. This one's up 17 centimeters from when we first discovered it. This one we just found recently. That's about 316 feet, and that's about almost 380 feet. Now, we were interested also in knowing how old they are. And it turned out it's not a simple task to figure this out. So we needed the cores to get things like bark and sapwood and heartwood. We also needed them to figure out how old they are and how much they're growing. So when you're up in a tree and you're coring and you're pulling out that delicate little core, well, first you feel a little bad for punching a hole in a tree, especially at trees like these. So you don't want to drop this core. And they come out and you're just like, taping them onto the mount. We've dropped very few. And then what you get is a slice. And you've seen this from Allison's talk. And from this record, you can actually figure out how old the tree is. And I want to explain this process to you. So here's a core series that came out of a tree in Mountain Home State Demonstration Forest that had 1,200 rings on it. So the radius of it from the center of the trunk, the pith, to the core, the outermost edge of the core, was here. So it was about 1.6 meters radius. So this is a big trunk. Because Allison was able to cross-date these rings, we can say what was the radius of this trunk every year of its life into the innermost ring 1,200 years. And this is the trajectory of that change in radius. Now notice we didn't get to zero. We didn't get to pith. You can't reach the pith. So what you really have to do is figure out how many years is it likely to continue from here to zero wood radius. And you can't assume it's linear. So what you can do is if you have a sufficient population of trees of different sizes, you can empirically derive this rate of change. So what you do is you note that over large stretches of this time series, it's roughly linear. You can take the midpoint of that, you know what size it is at the midpoint, and you can calculate the rise over the run, the number of years per meter as the change in radius. So that's one. So you pull those midpoint slopes. Here's another tree. We had 800 years on this core series. We went back not that far from the pith. But again, there's some linear portions of this. You pull the midpoints, take the slope. Here's one where we reached the pith. 200 some years in this series. There's the slopes. There's the midpoints. And in the end, you get these slopes, and you can plot the slopes in years per meter against the radius. Now notice this is not a linear relationship. It's curvilinear. It's a power function. So if you have a certain distance in wood radius left, you know you get as far in as you can on the wood radius with your core, and then you can fall down this curve and estimate the number of years required to reach the pith. Now this is at 50 meters. You develop these relationships for multiple heights, and that's the key. So in this particular forest, these are the power functions developed for these heights. And Allison mentioned we core the trees at regular height intervals. So you have your core series. You can then use these power functions to calculate how many years would have elapsed between the innermost ring and the pith. And then what you come up with is an estimated age of the trunk at each of these regular heights. So here's a monster tree. At 10 meters above the ground, the trunk's estimated age is this. Now what you can do, because what we really want to know is how old was the tree when it's established from a seed? Well, what was its height when it established from the seed? The y-intercept. Boom! Here's another one. Now, you can't really know how old these trees are without cutting them down and counting the rings. This is a way you can approach it, and this estimate is conservative. Here's another one. 1,000-year-old tree, a youngster. Here's one. The black means we actually reached the pith there, so that's a certain age. That's about 250 years old. So that's our approach. That's how we got these ages. And there's the final tally for giant sequoia. You see our trees ranged in age from 40 to 3,240. That's the old one. Now, there's been giant sequoia stumps with more rings than that. Not that many more. It's pretty old. And those are those two suppressed trees I was talking about. They're old for their size. Coast redwood. We didn't really have that many young ones. In old-growth forests, the little trees are actually older than you think. About 110 years, but look at this little guy, 230 years old. And up to about 1,840. Now, these are the 55 trees that we climbed and mapped all of their branches. There's about another 41 that we climbed and mapped the trunks and the reiterations and also cord. And in that set, it includes trees that are considerably older than that. In fact, Ken Fisher and I were out in 2008 doing a scouting mission. And we stumbled upon a tree, coast redwood, that was in an upland location. And both of us just were pretty much astonished that this tree was there, where it was. So this is the tree that we climbed and cored 200 feet above the ground. And that's the trunk that reached the year 328 AD. So 200 feet above the ground, and you didn't even reach the pith, and it was 1,700 years in. This limb, by the way, is pushing 2,000 years old. It has an epiphytic Douglas fir growing on it. So this tree turned out to be 2,500 years old, minimum age, which is a record. So to answer this basic question that we have, well, coast redwoods can get over 2,500 years old, but trees greater than 1,500 are pretty rare. Pretty rare. This one here isn't even 1,500 years. Giant sequoia, I would say trees greater than 2,500 years old are pretty rare. The biggest trees in the forest, many of which we targeted in our plots, were almost never that old or older. Of course, this one was. This one wasn't in a plot. This is on a paved trail. Okay, so I want to talk now about growth. We now know how big they are, how many leaves they have. We know at least how old they are. Then the question is, how much are they growing? Now, there's a geometric consequence of tree growth that's just an inevitability. And it has to do with as the circumference of the tree expands, trees are laying down wood over a greater and greater surface area. And one of the inevitable consequences of that is as you approach from the cambium to the pith, as you approach the pith, the rings get bigger. This is true for small trees. You've seen this on stumps. It's also true for very old trees. So here's one from Big Sur that was killed in the 1999 fire. You can see it has very small rings, and then the rings widen as you get to the pith. So radial growth, ring width, declines as an inevitable consequence of age because of development and geometry. So here is a view of that for both species. So what I've shown on the y-axis, the vertical, is ring width. And this is basically the volume growth divided by the cambium surface area. So this is kind of like a tree averaged ring width. So if you take cubic meters of volume growth divided by square meters of cambium, which is producing the growth, you're left with meters. Multiplied by 1,000, you get millimeters. So giant sequoia, much more orderly progression. Drops, so by the time you get to about 1,000-year-old tree, the rings are about 1 millimeter wide. You see a lot more noise in the coast redwood. This is a shade-tolerant species, a lot more differentiation in the stand development. You get a lot of trees that kind of languish, so there's a lot more noise. But inevitably, ring width declines as trees get older. Now, despite this decline in ring width, the rate of wood production of the trees continues to increase. So ring width is not a good measure for growth because it's geometrically constrained. This is the volume growth in cubic meters of the main trunks of these trees, plotted against age. Now, I've separated them into three classes. These are like the emergent trees that are the site trees. They've got all the resources they could want. And then on the other end, these are the ones that are overtopped or in bad shape. Regardless of which type of tree you look at, there's an upward trajectory as the trees get older. Now, this upward trajectory is, as the trees get older, they get bigger. And as they get bigger, they make more wood, and that the rate of increase in wood production continues to increase through old age in these trees. So the oldest trees in the woods, the biggest trees, are making the most wood. You'll notice a flattening off of this curve. Remember, this is just the main trunk. We didn't core all the branches. Well, wouldn't that have been a nightmare? This is just the main trunk. So I'll talk about the appendages in a moment. Another way to look at growth as a function of age is because we have such good estimates of the tree's mass, and because we have their age, you can kind of look at it as a chronosequence. You can say, well, over time, how does the tree's mass change? And because they continue to produce more wood as they get older, the rate of wood production increases, the mass is nonlinear upward curve. The cool thing about this measure, kind of reconstructing growth, is it's including everything on the tree above the ground, all the branches. And what you see here is that a 2,000-year-old coast redwood is considerably larger than a 2,000-year-old giant sequoia. They behave similarly for the first 600 years or so, and then they diverge. Coast redwoods grow faster. That is that. And that one is that. So, to answer this basic question, well, as they get bigger and older, their rings get smaller. But their volume growth continues to increase through old age. So the biggest trees in the woods are growing the fastest, if by growth you mean wood production. Why are the old trees still growing faster? They have more leaves. So here's leaf area of the trees plotted against the age for both species. Now the relationship's not tight here, but older trees have more leaves. Now a lot of us don't think in terms of square meters of leaf area, but a lot of us think in terms of area like acres, right? Here's acres. A tree with 2 acres of leaves. My yard's a third of an acre. This tree right here has 2.36 acres of leaves. Now, why do the tree's leaf area get bigger as they get older? Is it because they're getting older? Nope. It's because they're getting bigger. Kind of an obvious point, but it's a much tighter relationship with trunk size and leaf area. Now, a lot of us don't think in centimeters Btb. So let's think about it in feet. There, you get to, in both species, you have trees that are over 15 feet diameter that have over an acre of leaves. More leaves, more growth. They have a lot of leaves. I mean, they're opaque, some of these trees. These are not giant sequoias. These are coast redwoods in Jedediah Smith. Look at them. My God! Look, there's a little spruce. Well, it's not little. It's 90 meters tall. But look at these things. 2 acres of leaves on a tree. Means the tree grows a lot. So let's look at growth more closely. So because we were able to figure out their age and we could actually have the cross-dated time series, we could skin the trees back in effect and take each layer of wood away and go back in time. So here's main trunk annual growth in volume versus year and tree age. So here's a 350-plus-year-old tree, little whippersnapper. And this is its history of annual volume growth. We were able to take it from when its trunk was this big to back when its trunk was this big. Not climbable at this size. But you can see its rate of wood production is just increasing as it gets bigger. Not surprising. Well, let's look at a real old one. So here's the oldest, or the biggest coast redwood that we completely crown mapped. A tree that's not quite 1,400 years old. What a gnarly tree this is. And we were only able to take it back to when it was about 800 years old or so. But that's its history of growth from about 800 years to 1,300 years. It had some ups and downs. Well, there's that 1739 year, bad year. Now, I wasn't able to quantify the growth of all of it. I was just able to quantify the growth of these two big reiterated trunks and the main trunk. So all the appendages were left off. So here's how big the trunks were when we measured it here, and then back to when in the year 1500. That's how big it was. Now, of course, what happened in the first 900 years of the tree's life? Well, we don't know, but we know how big it is. 900 years, or we know how big it is in the year 1500. And based on our population estimates of wood production, this is its rate of wood production, on average, to get as big as it is this year. And then here's its history afterwards. So it had some tough times. Maybe crown fires. This tree had charcoal in it. They all have charcoal in their crown. But look at its growth now. Geez, that's a lot. It's a cubic meter of wood in 1 year. But this isn't the record tree. The record tree, I had to show you this record tree. We stumbled upon this tree, and it just blew our minds. So here's the growth history of this tree. I'm going to move on here. But it spent the first 900 years of its life growing at a pretty modest rate, capping out about 0.4 cubic meters a year. And look what it did. Now, it's putting on almost 2 cubic meters a year. Good God. Look at the crown on it, though. This is one of these trees that has almost 2 acres of leaves. Okay. Oh, and there it is. Oh. Golly. Well, it's one of these emergents. You know, it's got everything going for it now. It finally busted up above everybody else. It's like, yeah, now we're talking. So then we have a giant sequoia, the same sort of situation going on. So let's go into this stand. Let's look at some of these little guys. So here's a 250-year-old tree. Beautiful little specimen. We were able to take it back to when it was only, 30 or 40 years old. And here's its history. Again, it's increasing as it gets older. More leaves, more growth. It's all good. But what about this one? Ugh. Okay. Well, there's 1580. Bad year for it. So 3,200-year-old tree. We're able to take it back to when it was 2,200, which is a small stretch of its life. But there you have it. So trunk was this big when we mapped it for National Geographic, and we were able to take it back 1,000 years ago to when it was this big. Top is dead in both cases. But of course, that's a very small stretch of its life. So there's its full trajectory. In order to get to be this big, when it's 2,200 years old, its rate of wood production had to be this. What do you see? Well, this keeps. It goes through its ups and downs. There are fires that probably burn away leaf area. The trees need to recover that leaf area. And the main trunk's not super high priority for investment. If it's got to build leaf area, that's where the resources go. But look at it now. Look at its rate of wood production now. Almost a cubic meter. Pretty impressive. And there's Bob Van Pelt's drawing of it. Isn't that nice? Now, again, I want to emphasize that all that I've been talking about with growth is just the main trunk, because we didn't access all the appendages. This tree, and a lot of these big trees, have humongous appendages. This one is 6.9 feet diameter limb. That's 3,000 years old. We know it's that old because the trunk is that age where it comes out, and it's an original appendage. Imagine how much wood this thing's producing. So what we really need to do now with these RCCI plots is we need to go back in after 5 years and map them again. But that will give us the ability to really answer the question, how much wood are they really producing above the ground? We found in previous studies that in trees up to 1,500 years old, that by the time they get that big, 40% or more of their wood production is in their appendages, not their trunk. So this is not a trivial part of this equation. And I would bet you in the champion over there and here, it's more like 50 or 60% of their total wood production is not in their trunk. So we've got to do that to really get at this issue of total wood production and carbon sequestration. So to answer this question about old age, as these trees get old, I've shown you they keep growing. So are there any negative consequences? Are trees like us, they get old and that's it? They slow down and they're done. Well, eventually, yeah. So there is a negative consequence of it. They die. But as long as they're increasing in size, as long as their leaf area is expanding, the rate of wood production is going up. Now, another question that you might have about trees is their performance now like their performance in the past? And of course, that's a question that we've all been asking. So to get at that question, I've examined the earliest 100-year period that we have adequate replication for both species. In this case, we have about 30 trees of both species where we have these gray lines are traces, those, like the blue line in my previous slides, of their annual trunk growth history. That's the trace. And then the fitted lines are the trend. If it's colored, then it's statistically significant trend. So the blues, significant positive trend, red, significant negative trend, blacks, not significant trend. So during the period before the Industrial Revolution, the 100-year period, we'd expect as trees get bigger, the rate of wood production should go up. So over a 100-year period, on average, trees should be producing more wood. So there should be a positive trend. What you see is that trees have their ups and downs. Some of these trees, maybe we're recovering from fires or we're going into suppression. But look at this. There's the oldest coast redwood, and there's the oldest giant sequoia. They had upward trends. Is there any systematic shift toward a downward trend of growth as they get old? No. But what about the most recent 100-year period? And I think this is going to shock you. So these same trees shown here, this is their most recent 100 years. Now, some of our trees didn't go back to 1751. Here's the rest of them. Now, in this complete data set of all of our trees, only 2 trees have significant negative trends in growth in the last 100 years. This one, totally suppressed tree underneath a giant tree. It's in the deepest of shade. Barely making it. This one, also suppressed. Roots are being swamped. It's got a lot of, it's standing in a kind of a swamp, a skunk cabbage swamp. So it's got a tough time ahead. But do you see any change in the slope of the upward trend as you get old? No. No systematic change. Look at this tree. I thought that was really remarkable. So these old trees in the woods, they're growing faster because they're getting bigger. But maybe there's something else going on in the recent decades that they're going even faster. Now, part of this could be fire suppression. What happens during fire? The crown is reduced. The tree needs to rebound and rebuild its leaf area, so it's going to be investing less in the trunk. What have we done the last 100 years? We've suppressed fires. There haven't been that many crown fires. So maybe it's just the fact that the trees are just got more leaves. And they're just taking advantage of it in the absence of disturbances. So we have a poster in the session that I'd really like to chat with you about, looking at some of the specific results. Here's all 66 redwoods put together. This is the total signal. Now, I've already convinced you, I hope, that as trees get bigger, they produce more wood. So if we plotted a time series of wood production, you'd expect it inevitably to go up. Well, I took that out. This is size detrended growth. This is taking the volume growth of the tree divided by the radius of the trunk producing it. So big trees, you divide by a big number. Small trees, you divide by a small number. It takes out the size effect. This preserves the trend of growth, but not the size increase. The blue line is Allison's interannual growth ring index, just as comparison. And both of them are standardized by the standard deviate. So you can see how anomalous a given year is. this is one of the things that's worth discussing when we get together, because I have one of these chronologies prepared for each of the sites. And we can look and we can see some interesting stuff going on. And what's causing this change in growth? Is it something that we've done? Is it fire suppression? Is it climate? Well, those are really interesting things to discuss. But I can just say this, that the redwoods, taken as a whole, in the old growth forests of California, are growing faster now than they did in the past. What about giant sequoia? Well, here's all 41 of the giant sequoias. Now, one of our sites where we have actually quite a bit of replication is a place called Whitaker Forest, which was partially logged in the late 1800s. Right about here. These trees experience what appears to be a growth release in response to logging their neighbors. Less competition, more resources for the trees that are left. Hell yeah. Right? And then, as the trees came in around them and filled up the growing space, they returned to normal. But you'll also notice this interesting uptick here at the end over the last 100 years. So there's lots to discuss here. But I think we can say this. In answer to this question, does a tree's responsiveness to a changing environment diminish when it gets old? And I think clearly the answer to that question is nope. Which is cool. Thanks.